Okay, so these are a little bit odd beasts, improper integrals. What are they? Um, let's actually just do one of these right away, and we'll kind of see, go back and sort of read what all that stuff is above. What is an improper integral? Okay, so any integral that has infinity as one of its bounds is by definition improper. And again, if you think about what a definite integral is actually, asking for, like if I were to just draw what this quantity here represents, what does this represent? It represents the area under a curve. Well, what curve though? That infinity kind of makes this a weird curve because it seems like if I have a, a curve that just goes on forever and I'm asking for the area under it, it seems like the area should be probably infinite, right? I mean, at least common sense would lead us to believe that. In fact, if you look at it, if you look at the function 1 over the square root of x, what does that look like? Kind of like the reciprocal function, right? Something like this. It just goes on. So when I'm asking for the integral from 1 to infinity, I'm starting right here. That's my left bound. But then the rest of it is just all of that, like all the way to infinity, right? So it seems like, why would we even bother with this? Because how can that not be an infinite area? Well, it turns out that, strangely enough, what looks like an infinite area can actually be finite, strangely enough. How do we tell when we get that situation where it is finite? So this is the procedure. When you have an improper integral, you have to kind of use limits on it. So we go 1 to infinity of um, dx over the square root of x. What the first thing that we're going to want to do is change it into something that we can actually do. And that is, well, actually a combination of two things that we already know how to do. That is a limit, as b in this case goes to infinity, of an integral where I replace the infinity with that b. Okay? And then what that does for us is it changes the integral into just a regular old definite integral, as in it's got a number at the top and it's got a number at the bottom, right? We know how to deal with those. And then we also know how to deal with limits at infinity. So basically what we're doing with improper integrals is kind of changing it into two things that we know how to do, how to deal with. Okay, so now how do we go about doing that? Well, now that it's just a regular improper integral, and the limit will just sort of save until the end there. Now that it's just a regular improper integral, we know how to deal with those. We just do the fundamental theorem of calculus. That is, find an antiderivative, plug in the bounds. Okay, so the antiderivative in this case, if I raise that by 1, I get 1/2. So I'll have to put a 2 in front of it. So I get 2x to the positive 1/2. And then I have to plug in the 1 and the b. Now that's just the square root of x, right? So what I'll end up getting is the 2 doesn't even matter. I can pull it outside there. Now I'm going to plug in b there. So I'll get the square root of b. And then I plug in 1. I get minus the square root of 1 is just 1. And so that now I've done the improper integral, or sorry, I've done the definite integral part of this using the fundamental theorem. Find the antiderivative, plug in the bounds, subtract them. Now I can do the limit. Okay, so now what is the limit as b goes to infinity of the square root of b? That's what we're really asking here. You can think about what the square root function does as x gets very big, or in this case as b gets very big. It goes to infinity, right? The square root function is like that, but it continues to go up, 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 right? Forever. So this is infinity. So in this case, common sense seems to have prevailed. What looked like infinite area really was infinite area, so no problem. But as we'll see, that's not always going to happen. Now, what happens? What do we say about this when we see infinity, or that this limit just doesn't exist for some other reason? What we say is that this integral diverges. Improper integral diverges. So that's a term that we need to familiarize ourselves with. Divergent improper integral means that when we evaluate it, we get either infinity or negative infinity, or that the integral doesn't exist, the limit doesn't exist for some other reason. Okay? Now, suppose that we didn't get infinity, that we actually got a finite number. Then we would say that that thing converges. Okay, so if it converges, that means it's actually equal to a finite number. And what we're going to see this concept again of convergence and divergence later on in the semester, at the end of the semester, in fact, when we start talking about sequences and series. Okay, so let's try another one. Now this type of improper integral that we just saw, where you see infinity as one of the limits, or one or both of the limits, that's called a type 1 improper integral. So as soon as you see infinity on either bound or on both bounds, that's called type 1 improper integral. There's also another type of improper integral called type 2, which we'll see in a minute here. But let's try to do number 2 first, and we'll see how do we deal with infinity at both bounds, both upper and lower bounds. Okay, so the one we just did is sort of the intro, infinity just on one bound. Number 2, here we've got infinity, but on both bounds. So this is like the area under the curve for the entire real number line. Again, so if you were to draw this, in fact, I'll just go ahead and try to draw it real quick. The curve looks something like this. It's, in fact, a pretty common type of curve. In fact, this particular integral that we're doing here, if you go on and take like an advanced statistics class, you would probably see this integral showing up, this type of improper integral. Because that curve that you see there is a classic bell curve or normal distribution, something like that. And so what this integral would represent then is the area under this curve for all real values of x. In other words, on the entire real number line, what is that total area? Again, it looks like, how can that not be infinity? But as we'll see, it may not be. So how do we deal with an improper integral with infinity on both the bottom bound and the top bound? So the trick here is to split it up as two integrals, and we have to pick a value that lies somewhere between the two bounds. Well, the two bounds are both infinity, so we can really pick any real number. Well, the best real number to pick, as you can probably guess, is 0. So 0 is our breaking point there. We're going to split this up into two integrals, one that goes from negative infinity to 0, the other that goes from 0 to positive infinity. Okay, now how do we deal with this? Well, both of these then would have to be done in the same method that we did that other one. That is, change the infinity to a b, or whatever letter you want to use, and then take the limit as b approaches infinity. Now, what we can notice to make this problem a little bit easier on ourselves is that it is actually, choosing 0 is a really good thing to do, because look, it's symmetric, right? This half here is the same as this half here. So if this thing is a convergent integral, then whatever I get for one of these, I can just double it and get the area of the other one. See what I'm saying? So we only have to end up doing one integral here. But in general, if this were not symmetric, you would actually have to figure out both of them. So let's do the second one. And then if we do find out that this thing is convergent, then we will, so this is integral number 2. Let's do just that one. If we find that this is convergent and we get a real number, then we can just double it, and that will be the value for the whole thing. So integral number 2. Again, this is one where we need to remember that form, and so I wrote it earlier, but I'll write it again here. If you have this type of integral, du over u squared plus a squared, then it's this, the antiderivative is 1 over a inverse tangent of u over a. Okay, so noticing that that's the same form that we have here. U is just x. A in this case is 2. And so what we're going to get for our answer is limit as b goes to infinity of 1/2 inverse tangent of x over 2. Any questions about that? And in fact, that integral is one of the ones on that list, right, from 7.5. You notice number 17 was the one we just used. Number 17 on the list. Okay, so that means the next step is to plug in the 0 and the b and subtract. So plug in b, 1/2 inverse tangent b over 2. And then the other one, when we plug in 0, we're just going to get 1/2 inverse tangent 0. But the inverse tangent of 0 is 0, so this is actually just equals 0 anyway. That's gone. And so the question is, well, what the heck is the limit as b? What is this then? What is 1/2 limit as b goes to infinity of the inverse tangent of b over 2? So think about what the inverse tangent function looks like. This is actually one that kind of has to be done by graphically by looking at the graph. So think about what the inverse tangent function would look like. If I were to graph y equals the inverse tangent of b over 2. And then this would be the b axis here. So remember how the arctangent function looks. It's got horizontal asymptotes, right? Because I think I already went through that in sort of quick review of the arctangent function. It looks like this. And then this value here, where those horizontal asymptotes actually are, they occur at pi over 2 and at negative pi over 2. Now the fact that that's b over 2 doesn't really affect anything, because if you remember from pre-calculus, if you divide the variable by a number, that the effect that has is to stretch out the function horizontally. That's that b over 2 I'm talking about here, the over 2 part here. All that does is the effect it has is it stretches out what the function would have looked like without the over 2. So it's going to sort of be a horizontal expansion, but that doesn't affect the horizontal asymptote locations. The only thing that would affect that is if I had a number out in front here. Like that would change where those asymptotes actually are. Okay, so that means that this limit must be what? Well, as we go to infinity, it's approaching that horizontal asymptote there, right? Approaching this horizontal asymptote as we get bigger and bigger. And so that means the limit must be pi over 2. We're going to get 1/2 pi over 2, which is pi over 4. Now remember, what does it mean then when we what does it mean when we get a finite number for the answer for this kind of thing? It means that this thing is a convergent improper integral. Okay, convergent improper integral. And we just said that overall, if we got some answer, some finite answer for one of these integrals, right? Up here we called this integral number 2. This was integral number 1. Remember that we said it was symmetric. So what we got for integral number 2 will be exactly the same thing that we get for integral number 1. And so we know by symmetry, our final answer here is going to be integral from minus infinity to infinity of dx over x squared plus 4. By symmetry and by the answer that we just got, it must be twice the integral the answer that we ended up with, which is pi over 2. So interestingly enough, the entire area under that curve that I drew at the beginning, what's that drawing up there? Yeah, this area up here, all of that area is pi over 2. Looks infinite, it isn't infinite, strangely enough. Okay, so this number 3 is our first example of the other type of improper integral. And why does this end up being called improper? It looks like there's no problem, there's no infinity on the bounds or anything like that. But if you do notice, there is a problem with one of the bounds, because when you plug in that bound 3, what happens? Yep, square root 0, and the problem with that, I mean, square root of 0 is 0, so there's no problem with that, but the problem is that it is in the denominator, right? And you can't divide by 0. So that's where the issue comes in. That's why this is called improper. So try to get that straight. Two types of improper integrals, right? One of them, type 1, is obvious because you're just going to see infinity on either one bound or perhaps both bounds. That is, as soon as you see infinity on there, you know it's type 1 improper. Type 2 improper, a little bit more, you got to look a little more carefully because there's not going to be 0 on the bounds. What you're going to see is that you plug in one of the bounds and you're going to get a problem, an undefined, something that's discontinuous, right? A discontinuity in the graph, perhaps. And then there's even another thing you've got to watch out for, that it may be that the problem value is not at either bound, but it may be somewhere between the bounds. So that's the one that you really have to watch out the most for, because you might look, oh, there's no problem with the left bound, there's no problem with the right bound, it's not improper. But then you got to think, is there maybe a discontinuity between the two bounds? And that's the hardest one to spot, really. Anyway, for this one, how do you deal with this type 2 improper integrals? Well, you deal with it in the same exact way as the other ones. In fact, sorry, before we do this, let me just show you graphically kind of what that type 2 improper would look like. So if we were to graph this function, graphically speaking, why is it improper? What does it look like when you have this type of improper integral? Well, we're definitely going to have an asymptote on the function at 3 because it's not defined there. And the function that we're graphing is this one, y equals 1 over the square root of 9 minus x squared. If you plug in the number 1 there, or sorry, if you plug in 0, you get 3. That's 3 up there. If you plug in, actually, let me do it like this. I'm gonna make it, I'll call that 3 right there. And then as you get closer to the number 3, the function is just going to go up and up and up. So basically, you can see this kind of thing. So it's still that asymptotic approach, right? Like when we have the integral as x is approaching infinity, you're approaching asymptotically towards y equals 0. Same thing is happening here, only now the asymptotic approach is vertical rather than horizontal. But you can see that it still could potentially end up with what may be infinite area. But again, it may not be. So the only way we can really determine that is by actually checking, does it converge or not? If it converges, then that thing that looks like infinite area is actually finite. If it diverges, it really is infinite area. Okay, so how do we deal with this? Same way we did the other ones. Now we take the limit as b approaches the problem value, the value where we have this discontinuity. And in this case, we do have to be specific about the direction that we are approaching the number 3. Because if you see any number that's bigger than 3, if I were to plug in any number over here, 4, 5, or whatever over here, well, the function is just completely undefined over there, right? Because that would result in a negative number under the radical. So the function is not even defined at all to the right of 3. So we can't talk about the limit as we approach 3. We can only talk about the limit as we approach 3 from the left in this particular case. So it's a one-sided limit that we have to find here. And then you replace the problem bound with the thing that with b in this case. Okay, so that's what we have to do. That's the way we deal with these. Now for that one, if you notice, this one is another one where we don't even have to really do any work on the integral, because if you go back to your 7.5 table of integration formulas, I'm looking at number 18, integral number 18 on that list. Look what integral number 18 has. It's this, dx over the square root of a squared minus x squared. And what is that, according to that table, it is the inverse sine of x over a. Okay, so that means we just need to identify a here. A in this case is 3, and so what we're going to get, and then that has to be, we've got to plug in our 0 and our b there, and so we're going to get limit as b approaches 3 of the inverse sine of b over 3 minus the inverse sine of 0 over there is 0. So that's the limit that we have to find now. So the inverse sine of 0, the angle whose sine is 0, the angle whose sine is 0 is 0. So that means this is just gone. And now when we plug in 3 for b, we now can do direct substitution on that. We're going to get the inverse sine of 3 over 3, or the inverse sine of 1. And so which angle has a sine that is equal to 1? Pi over 2, exactly. So our answer here is, in fact, pi over 2. Interestingly enough, the same answer that we got for that last one, in fact. So this improper integral, this type 2 improper integral, converges, and the area that I have drawn here, this area here, you add it all up, it is equal to pi over 2, strangely enough. Okay, so here what we need to notice is if you check both bounds, 0, plug in 0, the cube root of -1, well, that's fine. The cube root of a negative number is defined. It's -1. And when you plug in 2, you also get something defined. So no problem at either bound. This is that one I was referring to, where you have to be careful with this type of improper integral. Checking both bounds, no problem. No infinity on the top bound, no infinity on the bottom bound. But notice that there is a problem right between 0 and 2, right? Right at x equals 1, we have a problem. Yeah, exactly, at x equals 1. So there's a discontinuity between the two bounds. So this is type 2 improper. And that, if you see that, where there's a discontinuity between the two bounds, this is always has to be considered improper. Well, this is another one where you have like the, you have, let's see, in this case, the problem's in the middle, right? But in that other one where we saw that sort of two-tailed one with the infinity and the negative infinity, it's similar to that. The way you deal with it is you have to split up the integral, and you have to split it up. In this case, you have to split it up at the problem bound, the problem. And then both of these have to be done separately. You say limit as b, in this case, approaches the number 1, because 1 is the problem bound. Now, if you think about the way this is going to be approaching one, this one is actually going to be approaching from the left. You have to do that. Replace the problem bound with b. And then the other one, now we're going to be approaching the problem bound from the other side. So this has to be a limit as we approach from the right. And again, b equals 1 is the problem one, so that's where we have to replace 1 with b. So that's it. That's the setup. That's what you have to do. Now, I'm going to show you graphically what this looks like, and then you can maybe see a little bit more about why we have to do those one-sided limits here. And we might be able to see if there's any symmetry we might be able to take advantage of. Okay, so if you think about what this function looks like, the cube root of x minus 1, there's definitely that asymptote at x equals 1. It's undefined there. If you plug in a number smaller than 1, like, say, 0, you get the cube root of -1, which is -1. So you're going to have that. And in fact, what the graph is going to do is go down kind of like this, approach negative infinity. Now, if you look at the other side, if you plug in the number 2 there, then you're going to get +1 as the output. And it's going to also approach that asymptote, but from the other direction. And so the graph is going to look something like this on the other side. All right, so there's no like symmetry around the origin or anything like that, but there actually is symmetry going on here. If you look at this, this region right here, if it is finite, is going to be exactly the same as this region right here, if it is finite, right? See that? So there is symmetry here. Symmetry, this and this are the same, except they're not quite the same because one of them would be below the x-axis, right? And one of them would be above the x-axis. However, in absolute value, those areas would be the same. All right, but now that actually, if you think about it, that actually gives us something we can work with, because if this integral converges by that drawing that I've just done, we know that it has to converge to a particular number without even doing any work here. What number would it have to converge to if this integral actually exists? So we didn't have to do any work, but I can tell by looking at that picture what the answer would be if this thing converges. What does it have to be? Again, it has to do with the fact that half of it's above the x-axis, but the other half is below. Zero, exactly. If this integral converges, it has to converge to zero. Does everybody see why? This part here is below the x-axis. So that's a negative area, and the integral is going to come up negative if it exists. This is above the x-axis, and it's going to come up positive if it exists. But we just said there's symmetry. And so since there's symmetry, that means this area here is the same as this area here, but negative. And so if you've got a positive area above, exact same negative area below, add those two together, you're going to get zero. See that? And so we know the answer already if it converges. If it converges, the answer is zero. Alternatively, if it doesn't converge, well, then it's nothing. When we just say this thing diverges, okay? And so that's another thing just to notice about improper integrals. If any part of the integral diverges, you have to say the whole thing diverges, okay? All right, so what does that tell us as far as like how we're going to approach this? Well, it just tells us that if I want to know what the value of this, if I want to know if this thing converges or not, I just need to do one of these. So let's just do the second one. And if this thing converges, then I'll know the other one does too, and then I'll know the answer has to be zero. Let's try to do this second one only. Okay, so to do that, this is just, again, you basically just treat this as you would a normal definite integral. In this case, we can do a u substitution. U is equal to x minus 1. Du is just equal to dx. And so the lower bound now, we'll have to change the bounds as well. Remember that when you make a substitution with a definite integral, those bounds are x bounds, right? These are x equals. And then if I want to figure out what the u is that corresponds to that, I just plug that into there. So my new bounds on my new u integral are going to be lower bound b minus 1, upper bound 2 minus 1, or just 1. And then we'll have du over the cube root of u. Then we can rewrite that to use the power rule, u to the minus 1/3 power. And then the power rule says that's going to be, if I raise that by 1, I'm going to get 2/3, right? And so then I'll have 3/2 u to the 2/3 power, and then I'll have b minus 1 here, and then I'll have 1 here. So plugging that in, I'm going to get the limit I need to find. Now, and notice that you can do direct substitution here. If you plug 1 in for b there, you get 0. Right, so that term is just going to be gone. And then if I, well, that just leaves me with, right, 3/2, right? That's it, 3/2. So what does that mean? Well, that means that this thing converges, right? And so what's the final answer for the integral then? what is the integral from 0 to 2 of dx over this cube root of x minus 1? Well, I think we already mentioned that since it did converge, then if we did the other integral, we were going to get negative 3 halves. And then adding that to the positive 3 halves, we'd get 0. Oh, and one other thing I just wanted to point out about this. Suppose that you didn't recognize that this was an improper integral. Suppose that you just plowed through the whole thing saying, I didn't notice it's improper, and I just went through and did the work. In this particular case, I believe you would actually still just get 0 for your answer. However, if you did that on the test without showing any indication that you knew that it was improper, what do you think you're going to get for credit on the test? So my question is, if you didn't notice it was improper, and you just plowed through and got your answer of 0, which I think you would, how much credit do you think you're going to get on that without noticing it's improper? Even though you happen to get the correct answer, perhaps. Well, very little. You may get a few points for doing the antiderivative correctly or something like that, but very little credit, because you don't know if it's going to diverge or not, right? And suppose you didn't notice that it was improper, and it diverged, but you said that it didn't diverge, and you got a wrong answer in that direction. It shouldn't really matter whether you happen to get the right answer by chance, just happened to converge, or you got the wrong answer because you didn't notice that it was improper. So you understand what I'm trying to say here. You got to notice that it's improper. On the test, I'll actually tell you, evaluate this improper integral, but just for reference, you gotta show the work to say that you understand that this is an improper integral. And what do I mean by that? What is telling us that this is improper in your work? What are we going to do here that we wouldn't do if this were not an improper integral? We're putting that, right, and the b there, and we're splitting it up into two integrals, right, and finding the limits of both of them. And so that is what's telling me that you know that it's improper when I see the limit on there and the b, or whatever letter you decide you want to use there. Okay? So just understand that improper integrals have to be treated in this particular way. All right, so let's do the problems now. So this one, just typical improper integral with the infinity on the top. Okay, so remember what we need to do here on the type 1 improper. It's obvious that the problem bound is the one that has infinity on it, so we take a limit as b goes to infinity, change the infinity to b, and then maybe write this as a power function so that we can integrate it. Okay, so this one's fairly straightforward. And then here, power rule says to raise that to the negative 1/2 power, so that means we're going to put a negative 2 in front. And remember on these improper integrals that you definitely have to treat it as an improper integral, meaning you definitely need to put this limit stuff like we're doing here, otherwise you don't get the credit for it, or you don't get most of the credit for it. Okay, so this one you might want to go ahead and just write that with a positive exponent so you can see what's going to happen as b goes to infinity. This is going to end up being negative 2 over the square root of b. And then I think it's hopefully pretty obvious what happens when b goes to infinity here. This term is going to go to 0. That leaves us with 2 for the value of the integral, and therefore it converges to the number 2. Okay, integral negative infinity to 0 of e to the 5x. Okay, so in this case, type 1 as well, the infinity is on one of the bounds, so we just know immediately that that's what we have to replace with b, and in this case we don't let b go to negative infinity, and then we put b down here. And this is being evaluated from b to 0, so plug in 0 first. If I plug in 0 there, I just get e to the 0, that's just 1, so I'm going to have 1/5 and then plug in b. Okay, now think about what happens when b goes to negative infinity here. Negative infinity. So b is going to negative infinity. That's where the b is, right? So what's this ultimately going to be? We're going to have a large negative power there, right? But remember that if you have a negative power, that's the same as if that term were in the denominator, right? And so that means this whole thing we have to view as being like 1 over e to the 5 times a very big number, right? And what happens as b goes to negative infinity then in this case? What happens to that whole term there? Basically like having 1 over e to the something with a big power, right? So what happens then? Well, that means that's going to go to 0. All of that goes to 0. And so it goes to 0 exactly. And so that leaves us again with just the other number that was there, 1/5. So again, this one does converge, and it converges to 1/5. Okay, so problem 3 is sort of demonstrating like what I was just talking about, where you may have one problem that sort of combines a couple of the ideas that we've talked about so far. Like in this case, x e to the negative x, this particular integral, it's an improper integral, but in order to find that antiderivative, it looks like we're going to have to do integration by parts. So you can kind of see what I was talking about there. So here we'll have the limit as b goes to infinity, integral from 1 to b. Okay, and then to find the antiderivative here, we're going to have to do integration by parts. So let's do the indefinite integral first. That requires a little bit more work here than just like a substitution or a power rule or something like that. So we could say u is equal to, remember Liate for integration by parts, logarithmic function. Sorry if we don't have any of those. Don't have any inverse trig. We do have an algebraic function right there, x. So that's what we're going to have to make u be. And then dv can just be the rest of it, e to the minus x dx. So that means du is equal to dx. V is equal to negative e to the negative x. And so the integral then becomes, according to the parts formula, negative x e to the negative x plus, in this case, integral v du. That's just going to be this. And then that is, and the antiderivative there is another negative e to the negative x. Okay, so there's our antiderivative. Now we can go ahead and do the rest of the improper integral part of this. So the limit as b goes to infinity of the integral from 1 to b of all of this must be equal to the limit as b goes to infinity of this antiderivative that we just found. In fact, let's just go ahead and factor that negative out of there. I'll just put it in front there, and then we'll get this. Okay, then we got to plug in the b and the 1, so we'll get b e to the negative b plus e to the negative b. And minus, what do I get when I plug in 1? Looks like I'm going to get e to the negative 1, and then minus e to the negative 1. Okay, so then we have to think about what this limit is going to be. Now, in particular, actually, let's go ahead and rewrite this so that we can maybe see a little more clearly what that limit is actually going to be, or how we have to find it. So here we're going to have b over e to the b, right? And then the next one, 1 over e to the b. And then this is, there's 2 of those, right? Minus e to the minus 1, and then minus another one. So there's minus 2 of those, and we can write that as 2 over e. Okay, now here we do have to be careful. Anything that we've seen prior to this in any of the math classes, we have to remember, what am I talking about here? One of these limits is not quite so cut and dry as it might look. I think maybe we can see that this one is pretty obviously going to go to 0. But what about this first one? What's going on with that? Limit as b goes to infinity of b over e to the b. Well, if you look at it, you can kind of just think about plugging in. Yeah, that's true. E to the infinity does go faster to infinity, but there's a mathematical way for us to show that. But what we first have to notice is that when we just plug in infinity, what we end up getting there is infinity over infinity. Do we remember what that is, or what that should tell us? Remember that infinity over infinity is what is called an indeterminate form. Exactly. We've got to think about L'Hopital's rule there. This is an indeterminate form. So we can't just say that it's zero, although it will be, but we can't just say that because indeterminate forms require some demonstration of why the limit is what it is. And so that's why we have to use L'Hopital's rule here. And L'Hopital's rule says that when we have an indeterminate form like this, we can take the derivative of the top, right? The derivative of b is just 1, and then the derivative of e to the b is itself, right? So remember L'Hopital's rule. If you forgot what that is, go back and look at it because it's important. Anytime you have an indeterminate form like this, you do have to demonstrate L'Hopital's rule. And so that's on the test as well. Even if the limit is, ends up being what you think it is, you do have to show the work for L'Hopital's rule. And that's what this is right here. And so that, now once we do that L'Hopital rule one time, just take the derivative of the top, take the derivative of the bottom, take the limit again, now we see that this limit is clearly 0. But we did have to demonstrate that. And so that means this thing is going to 0. And so was the second term, but the last term then is not. And notice again, we factored that negative out and we have another negative there. So it looks like our final answer here, 2 over e. All right, so let's try number 4. So now we're moving into the other type 2 improper integral. In this case, I think you can see that one of the endpoints, one of the bounds of the integral is the problem value, right? 1 is, because when you try to plug 1 into that denominator, you get 0, and the division by 0 is a problem, right? So in other words, there's a discontinuity right at the left end, or sorry, the right end of this of the bound for the integral, the upper bound. So since that's the problem value, we change the problem value to b. We take the limit as b approaches the problem value. In this case, it has to approach from the left since b is the largest, the right endpoint of the interval that we're looking at, right? So we're going to be approaching that from the left from numbers that are less than 1. Then we replace the problem value with b. So that's the integral that we have to find now. This one we can do just a regular substitution. We can say that u is equal to x minus 1. Du is just going to be dx. And then remember that we have to change the bounds as well. And so the lower bound is going to become, let's see, it was minus 3. I have to plug minus 3 into here. So minus 3 minus 1 minus 4. The new bound there. And the new upper bound is going to have to be b minus 1. And then the integral becomes du over u squared. And then let's write this with a negative exponent so that we can use the power rule. So we get limit as b goes to 1 from the left. That's going to be negative u to the negative 1, right? So we're actually going to get negative 1 over u. As b goes to 1 from the left, I'm going to plug in the b minus 1 there, so I'm going to get negative 1 over b minus 1, and then plus 1/4. Okay, so now we have to think about, and this is probably a graphical type limit or a table limit. If you want to figure out what that limit is as b approaches 1 for the 1 over b minus 1. So graphically probably is the way to think of this, or a table. think about what 1 over b minus 1 would look like on the, if you were to graph it, right? So this would have to be like the b-axis. B minus 1 says that you're going to have an asymptote at 1. And as I approach 1 from the left, so this is 1 over b minus 1 here, I'm graphing. And again, what I'm trying to do is figure out what that limit is, right, when I plug in 1 right there. Well, you can probably see, even without a table or a graph, trying to plug 1 in there is going to get you something undefined. But graphically speaking, you can kind of see what happens there. B minus 1, in fact, we might as well even graph negative, because that's what this, there's the negative right there. And so think about what that would look like. If you plug in a number that's just slightly less than 1 there, say like, or even anything less than 1, 0, then you're going to get a positive number. So it looks to me like the graph of this function is going to do something like that. And so as you approach 1, right, coming closer to 1, the function is going up, up, up forever, right? So this is going to infinity. And so what do we say about this particular improper integral? It's divergent. This one's pretty tricky. In fact, I don't think we've actually done one like this yet, because this one is what's called doubly improper. Let's see why it might be considered doubly improper. Any indication about why we might call it that? Well, I think it's clearly improper right away just because of that, right? The infinity. But there's another reason that it's improper, and this is why we call it doubly improper, because it's also improper at the other end for the other reason, right? So that's the type 2 reason, right? The 0 bound and the square root of x in the denominator means that it's also type 2 improper. So it's both type 1 and type 2 improper at the same time. How do we deal with something like that? Well, just like with, well, we don't have to take a limit of a limit, but what we do have to do, just like that one where we had the infinity at both ends, right? It was still type 1 on both endpoints, but we had to do something to, well, make it doable, right? We had to split the integral up into 2 parts. So we're going to have to do the same thing here. The problem bound at the left is 0, so we're going to have to take the limit as, in fact, actually, before we even do that, let's do this. Let's split it up into the 2 pieces here. So we're going to go from 0 up to some number, and then we're going to have another integral from that same number to infinity. Now, the question about what that number is, remember, you can really pick any number you want here. And this one, unfortunately, there's really no way to know what a good number, like what, there is one number that's actually better than all the others for this one, but you really can't know that until you reach the end of the problem. So, but that's okay technically, because what you can do is say, well, I don't know what number that should be, but once you do get to the end, you could say, oh, look, it's pretty clear what the best number to put in here is, and then you can just go back and fill it in at the end. I'll just tell you right now that if I'm remembering correctly, I think the magic number here is 4. And again, I'll sort of point out at the end of the problem, like why that number happens to be better than any of the others. It's either 4 or 2. Michael, are you here? Are you here right now?
Here, but I don't recall what number that is.
You didn't try this one?
I did try it, but let me look at that real quick. Hold on.
I think it's 4, but even if it's not, we'll figure it out at the end here.
Yeah, no, I actually made an error in this one. I didn't treat the 0 end of it as improper.
Oh, okay.
So yeah, I screwed it up.
Okay, no problem. We'll figure it out here. I'm thinking it's 4, but I'm not 100% sure. So if it's not, we'll go back and change it. Okay, so let's see. What do we want to do now? So now we have 2 improper integrals, right? One of them is type 1, and the other one is type 2, right? By taking this doubly improper integral and splitting it up, we actually ended up with both a type 1 and a type 2 improper. Okay, so the first one, the problem value is 0, so we're going to take the limit as b approaches 0, and we have to be approaching from the right here, because again, we're approaching from numbers that are bigger than 0. And it wouldn't, in this case, it wouldn't even make sense to not put that plus on there. Because if we approach from the other side, we'd have a problem with that root, right? We can't approach from any number that's less than 0 there because it wouldn't even make sense. The other one is type 1 improper, and that one, I think obviously we have to put that as limit as b goes to infinity for this one. In fact, here we might actually, I don't know if we should even use the same letter here. Sometimes, well, it's two separate integrals. I think it's obvious that one b applies to one and the other b applies to the other. Okay, now for both of these, they're both the same integrand. So once we find an antiderivative, we'll be using the same function for both of them. So let's go ahead and again separately find this antiderivative, because that doesn't look like a particularly straightforward integral there. Like, how do we even find this antiderivative here? This indefinite integral. Let's see, what might be a good thing to do for this one for substitution? I think substitution is the way to go on this, but I'm trying to think, what is the substitution? Anybody have an idea about what to make the substitution here?
The substitution I did was t equals the square root of x.
That's what I was thinking too, yeah. Except I'm going to use u though. Root x, that's kind of what I was thinking too. Root x would be a good way to go. Now, for that, I think we probably want to find directly what dx is. And so typically what you can do, you can either take the derivative du at this point, or you can actually just solve this thing for x and then find dx that way. So that's what I'm going to do. I'm going to square both sides of this and get x is equal to u squared. And then I'm going to take the differential of that, that's dx is equal to 2u du. So that means this integral then is going to become, so the dx on top will become 2u du. And then in the denominator, we said that u is equal to the square root of x, so we're going to have a u down here. And then we also need to know what x plus 4 is, right? Well, x is u squared, so this is going to become u squared plus 4. This is a nice example of a substitution, a little bit more of a difficult substitution integral. Now, if we look at that and then we look back on our formula sheet, again, you will have this on the test. It will be attached to the test, in fact. If you look back at your section 7.5 table of integration formulas, that one is actually on there. That's number 17 on the table of integrals. So number 17 was a equal to 2. A equals 2. And that says that that integral is then 2 times 1 over a, so 1/2, arctan or inverse tan, u over a, right? So u over 2 here. And there the 2 and the 1/2 cancel, and we are left with, I guess this is fine. So we'll change this to inverse tan of what was u. It's square root x, so square root x. This is a good problem. It's showing kind of a lot of different stuff. Pretty difficult as well. This is probably one of the harder improper integral problems. All right, so let's go ahead and figure out what these are going to be. We'll do them separately. So that one, we found the antiderivative, so now we can plug it in. So we'll get inverse tan of root x over 2, and we're going to evaluate this from b4. And at this point, where is the table of integrals? So this is on section 7.5 in the worksheet packet. here, section 7.5. It's all those tables, all those integral forms at the top. Okay, and that's again what will be on your last page of your test. Okay, so at this point, I think we can see why the number 4 was probably the best choice here. And like I was saying before, if you didn't notice that and you just arbitrarily picked some other number like 1 or whatever, it would be fine to go back and say, well, I don't really like my first choice because it doesn't really give me a nice number here, right? And you can see why 4 is probably is going to give us a nice number, because now when we plug that 4 in here, right, 4 is getting plugged in there, we're going to get root 4, which is 2, and then 2 over 2 is 1, right? And that's why that 4 was a good choice, because now we have inverse tan of 1. Okay, now, what is the inverse tangent of 1? The angle whose tangent is 1. That's what I'm looking for. Think on your unit circle. That's the place where the sine and the cosine would have to be equal to each other, right? Because that's where you're going to get 1 from the tangent. Where are the sine and the cosine equal in the first quadrant? That at pi over 4. By the way, if you don't remember that, you're certainly welcome to use your calculator to do that. What you would do, since if you're in radian mode and it puts out pi over 4, it's not going to say pi over 4, it's just going to be some decimal. The way around that is to put your calculator into degree mode. If you put your calculator in degree mode and you say inverse tan 1, well, it's going to say 45 degrees, right? But pretty much in this class we almost entirely stick with radians. So at that point, all you'd have to do is say, well, what's 45 degrees in radians? Well, hopefully that's pi over 4. So that's a pretty good way to use the calculator to sort of help you with those trig ones. Put it in degree mode, find inverse tan or inverse whatever of whatever you're trying to find, then change it back into radians. Okay, but then we also have to think about what the limit as b goes to 0 is for this quantity here. Well, that's just going to be the inverse tangent of 0. But the inverse tangent of 0, the angle whose tangent is 0, is just 0. So that means that one is actually just going to go away. That one goes to 0, or is equal to 0. All right, so that leaves then the other integral that we have to do, right? The one b going to infinity from 4 to b. So we'll do limit as b goes to infinity, integral from 4 to b of the same thing, right? So we only had to find that antiderivative one time. It would be the same antiderivative, but now we just have a different limit to find. So this is the limit as b goes to infinity now of the inverse tangent of square root x over 2, plug in this case, oops, the 4 goes down there, right? 4 here, b here. Now we'll plug in the b, we get inverse tan of root b over 2, inverse tan, this is the same thing, right? We're going to get 1 there. Okay, now we have to think about what happens as b goes to infinity on the square root of b, the arctan there. So now we have to think about what that function is going to look like. So in other words, this might be one that we would want to do by a graph or a table, perhaps. Probably a graph. So if I graph inverse tan of root b over 2, what does that look like? Remember that the inverse tangent has 2 asymptotes, right? 2 horizontal asymptotes. It does this kind of thing. Okay, so now let's see, what are those asymptotes is the question. Does it stay as pi over 2? Yeah, okay, cool. So the asymptote stays at pi over 2. So that means that this limit here, that's going to be pi over 2. And then the minus the inverse tangent of 1, which we said was pi over 4. And so that ends up being pi over 4 then. Okay, cool. So that means that our two parts of this, both of them converge, right, on the both parts of this improper, doubly improper integral, right? And so putting this all together, final answer, we got pi over 4 on both of these, it turned out. The first part we got pi over 4. The second part we got pi over 4. So finally, pi over 2, final answer. But it is a good question because it demonstrates this idea of being doubly improper. It's got, using a nice substitution here and then recognizing you have to use a formula. And then this idea of like picking the proper bound when you split that integral up into two. And like I said before, if you did pick the wrong number there, and at this point right here where you said, well, maybe not the wrong number, but just something that wasn't so good, like when we were at this point right here, and we were trying to decide what that was going to be, like if I had picked 1 there, I would have got inverse tan 1/2. Well, what is that? That's not something that just sits on the unit circle very nicely, right? But inverse tan 1 does. So at that point, you might say, well, if I had chosen a different number, like 1 or something like that, maybe you'd say, is there a better number that I could have chosen? And then 4 is the better choice. At that point, you could have gone back and changed all of those bounds back to being 4 instead of being 1.